I'd like to welcome Carole Jackson, Director of the Netherlands Institute for Radio Astronomy. She's had a long career in radio astronomy, starting, I think, a PhD in Cambridge in a time when radio astronomy was really developing very fast, and worked a lot in Australia with the SKA project, which is another of these wonderful big science things that's all getting bigger and bigger. And she's going to tell us about big science and the universe, mega projects in astronomy.
Okay, thank you. Okay, thank you, and thank you for inviting me. And I'm going to take a certain tack through big physics and big projects in astronomy. So please excuse me if I don't mention your favorite big project. So yes, I'm based in the Netherlands. I'm very pleased to be Director General of Astron, which is probably one of the very biggest radio astronomy institutes in the world. It's a national institute. And yes, so to start. So I thought I'd start with this slide, which is a popular slide. Today's astronomy really answers some of the biggest questions in the universe. And it was great to hear the talks from the LHC and to understand that there is a merging. It's all about physics. The biggest questions, that we can think of: are we alone? What's happening in the universe? Where did everything in the universe come from? Based and can be answered around physics. Now, these are actually the questions that underpin the concept of the square kilometre array, which I will talk about because I've been involved in that for 25 years. But similarly, other big astronomy projects have similarly big science goals. So I'll show you where I come from. This is my institute, about 200 people based in a rural part of the Netherlands. It's very deliberately showing a picture of a telescope in the foreground. And whilst we're talking about big projects in physics, when this telescope was built in 1956, it was the world's biggest steerable radio telescope. That record lasted for a few months, sadly. It was eclipsed by Jodrell Bank, which you probably know is quite significantly bigger. That's 25 meters in diameter. But it's also a salient story in that we do build bigger and bigger things for quite good reasons, that we are trying to get higher sensitivities, or like LHC, higher energies. So we are pushed to the limits of engineering. But anyway, we're in a nice area and we're protected by radio frequency emission zones, which is quite nice. And I'll come to just talk a little bit about this dish was built with a very particular science purpose. The squiggly map on your right is one of the first maps of our galaxy made in H1, in neutral hydrogen. And that was the science driver for spending a lot of money at the time on that telescope. And it also points to the origin of, particularly for radio astronomy, the Netherlands is very strong in radio astronomy, and a few other countries, including Britain and Australia, coming out of radar in World War II. And this was strong in the Netherlands, particularly because scientists, astronomers, and engineers worked very closely together from the start. It was actually an astronomy-led enterprise. I think it's true to say in Australia, it was more of an engineering-led exercise. And you might see parts of that come through this talk also. So I'm going to argue that the universe is our ultimate big physics laboratory. If we can't detect it in the universe, well, damn it, we can't build a big enough laboratory. I'm going to talk a little bit about today's big astronomy facilities and projects, because I think there's a difference. I was particularly asked to talk very briefly about NASA. Joe's smiling because I had to then go and read up about NASA a little bit. And because it does give a basis, I think, on scale as well. And then I'll talk a little bit about the bigger future. So how is this impacting how we accomplish research when we have to build facilities that cost $1 billion or far more euros? What do we gain, and perhaps what do we lose? So just because we all like big things, here is a montage of some very, very big telescopes. Now, most of them exist. Some of them are not quite built yet. LSST is still underway, and JWST is the successor to Hubble, which will be launched next year. What I did want to leave you with from this impression is that astronomy is indeed the whole electromagnetic spectrum, from long wave, and I mean really long wave radio, tens of meters radio astronomy, through to gamma and X-rays, but now increasingly includes neutrino astrophysics, cosmic ray physics, and I have to say LIGO, gravitational wave astrophysics. So we are even moving beyond astronomy, where most people think of optical astronomy. Now, why do we do this? Well, we do this because we get the most amazing pictures. We can see all of the galaxies in the universe, depending which waveband you look at. But here's a beautiful image from Hubble, very, very deep field. So very inspiring science that captures our imagination and asks, seeks us to ask the deepest questions. And some of the things I've worked on, and I did want to just show this because I think it's a phenomenal movie. I didn't make the movie, but I worked on the survey that actually mapped all of these galaxies. This is the nearest 250,000 galaxies to our Milky Way in the universe. Now, this is a simulated fly-through, but if you don't feel small after looking at that, then I'm not sure how I can impress you. The universe is full of galaxies. The point is, how did we get here, and what does it mean? And perhaps even, what is dark energy? So, the whole of the history of the universe on one slide, starting from the Big Bang, indeed, through the very elementary particles, and to the formation of structures and stars and galaxies to today. And I'm standing over here, and this will be today, with very mature stars and galaxies. And we move from the era of high energy physics, CERN and LHC, indeed probe amazing physics down at the subatomic level, and astronomy gives us the view into the bigger picture, a big picture, and perhaps is the way to unravel the nature of dark energy and dark matter. So you might ask, so is astronomy really a big physics science? This was a report in Nature a few months ago that the numbers of papers with thousands of authors is indeed on the rise. Well, that's no surprise from our high energy physics friends, but this is increasingly true in astronomy. It is. And for that, I would say, I think there are three flavors of big astronomy today. There are the very big collaborations, which really are harnessing existing telescopes. So this is where we see big groups getting together and using multiple telescopes, not necessarily of the same type even, different frequencies, different inputs. A very good example of that is the Event Horizon Telescope. The second type, I think, of big astronomy are the National Institute-led telescopes and facilities. They're the ones, literally built by a country or perhaps one or two. And the third one is the really big astronomy, and that's the one I will dwell on the most, where agencies or IGOs, intergovernmental organizations, really do get together and fund billion-euro type instruments and facilities. So I'll do I'm going to skip over the first two of this type, but I will show a couple of examples just so we're on the same page. And talking of pages, you can always make news. This is fabulous. This was the mapping of, or the imaging of the black hole or the black hole shadow in M87. These are all the front pages of newspapers from around the world in May last year. So fabulous result. It's an amazing result, but 1,000+ collaborators to do that. So a phenomenal result, but not necessarily from, you can argue a little bit on that one, but what they did was very clever. They didn't go and build their own billion-euro facility. They mapped together 8 existing telescopes, agreeably including ALMA, which is €1 billion, but they got time concurrently on 5 instruments to be able to do this science. So in a sense, it's big astronomy, but done in a particular way. So very interesting. A little bit about big facilities. So a big facility, for instance, might be the VLA, the Very Large Array in New Mexico, built, owned and operated by the National Radio Astronomical Observatory in the USA. So that's been in place since 1973 and goes through successive upgrades. It's big, and sorry, I didn't go and check how much it cost to build, but it would be at least $1 billion to replicate today. And it's of a scale, and it is open to all astronomers, open skies, a bit, I guess, like CERN too. It's an open facility. And they are looking to build a next generation VLA now. And similar to this, for Europe, there is the European Southern Observatory, which does optical and infrared and millimeter astronomy. So these are the national agencies that can build instruments of significant scale. So they're the first two. So let's get to the really, really big stuff. They're really big mega projects and facilities. So the first one I'll start with is the birth of NASA. So NASA has its roots in the National Advisory Committee for Aeronautics, which was formed in 1915, so quite impressive. Very, very early days of aeronautics, formed to explore the boundaries of aeronautics for the world, if nothing else. And this is the, I'm going to have to read this, sorry, the Bell X-1, which was one of their first supersonic planes. Now, that was disturbed, if you like, by the launch of Sputnik. So along comes the International Geophysical Year of 1957, and Russia rose to the challenge and launched Sputnik. And it's exactly in that year that the NACA in the US became NASA, or was charged to become NASA, very much to enter the space race and the space years. So NASA was established in 1958. It has a mission of space exploration, but now increasingly, of course, also some Earth observation. And I think, and I hope we all know much of its history. I'm not going to tell you about things like Apollo, Skylab shuttle, the International Space Station, but I would point to it has increasingly missions which are actually telescopes. For instance, the Hubble Space Telescope, which had an estimated cost budget to launch of $5 billion, and probably another $5 billion to run over its now very long lifetime. And NASA is huge. NASA is of a scale that really, I think, is way beyond anything else we've seen so far. 17,000 employees and a budget of $21 billion per annum. And it's very active, across any range of areas. I put in a couple of different options. One is the Sophia radio telescope, the Sophia telescope, based on a jumbo jet, and this is the James Webb Space Telescope that will be launched next year as a successor to Hubble. And I'll also mention that a very, very strong set of missions, and these are just the exoplanet missions, doing exoplanet science. And even today, things are, I guess, getting so big and so complex and so many missions, we now see NASA and ESA working together. So the European Space Agency dates from 1975. United Space in Europe was founded with 22 members, but is significantly smaller with 2,200 staff and a budget of 7 billion euros per year. So they're the big agencies. So what I thought I would talk about, because I know a lot more about it, is the Square Kilometre Array. Because I'd like to give you now, having skipped over those because they exist and they've come from at least some history of 40 or 50 years, how do you build a mega project in astronomy today? How does it happen? How do you even invent an IGO to do amazing, next generation science? And this is the story of the Square Kilometre Array. I have a plot. This is the only plot I have with numbers on it. So what it is, though, is a plot of relative sensitivity across dates running from 1940 to 2020. And the dots on that plot are all radio telescopes. And what you can see, working up through history, is we can see the Dwingler telescope that I showed you where I work. You can see Jodrell was a major step in sensitivity. And you can follow that all the way through a whole bunch of acronyms, hopefully to the SKA, which isn't yet built. But the point on this being that we are on, this is the kind of trajectory that we look for when we're looking to make those next leaps in what can we explore, what can we do, or what do we need to do. So that very much set the stage of what the Square Kilometre Array needed to be able to do. Now, there's a long history with the Square Kilometre Array, which I won't go through, but I do want to touch on how it brought together, there were a lot of ideas in the 1980s of where do we go, if we go back to that one there. The VLA was well in place by 1980. So once, I'm afraid, astronomers build one telescope, they start thinking about the next. Sorry to tell you that. Anyway, so having built one big telescope and got it working really, really well, so what comes next? So the 1980s and 90s were very much an era of looking at what would be next. We know what we have done, we know what we can do. There was an OECD Global Science Forum in 1995, which actually included the Radio Astronomy Forum to look at, so what next at that level. And at the end of the 1990s, 1997, there was an MOU between a number of countries that you may not think are necessarily working that closely together at large scale to explore new technologies for radio astronomy. And that was really the seed for really doing a lot of exploration. Now, this is more or less engineering-led, because the astronomy ambitions as to what we would like to detect in the universe were so high, we really need some breakthrough technologies. So the story of the SKA is this tug between technologies and astronomy ambition. And I left on the last one, the year after that, the name SKA became to be adopted, and as you can see, it even has a logo. It's had a logo for some time now, 20 years. So by then it becomes part of the general story. So people can actually talk about this thing called the square kilometre array, although it was a very long time before it had a shape or a flavour, or what was it going to look like? What was it going to be? Because this technology exploration was quite central to its story. So here I made a quick sketch because I realised I didn't have this, but for those of you who like this kind of stuff in the room, there was, in the early 90s, everyone thought it was obvious you just build a huge array of dishes and you just build more and more dishes and you get a bigger telescope. But there was this time from the late 90s through to the 2010 or so, where in fact we went through quite an explosion through many countries working together, looking at a slightly broader range of options, and I've tried to break them into 4 sets there. The interesting two, I think, are the second two, the one where you don't have dishes, you simply don't have collecting dishes, you go back to dipoles, and on this very far side you have the more exotic ideas, of which I will show a couple. Now, the reason this was an interesting era is that it really allowed the engineers to be quite creative and to really explore some ideas that perhaps have got lost along the way from very early radar ideas. And this settled into a set of SKA precursors and Pathfinders, which are in themselves large telescopes. A few $100 million or more are being built or have been built by either single countries or groups already. So in fact, it spawned its own generation of new telescopes. So just to finish the story of, so where is the SKA, because I don't want to leave you hanging before I show you the exciting technologies. A real legal entity was formed I'll skip to 2011, formed of these countries, you can read them off: UK, Netherlands, Sweden, Italy, Canada, Australia, China, India and New Zealand, and a whole raft of observers. But that was an official company formed by those governments to continue the exploration and the design of the square kilometre array. And since then, last year, the actual IGO treaty was signed. So from 2011 to 2019, we then went through a process by which the government said, we want this to be an IGO, it needs to be an international governmental organisation, and it will start construction in 2022. And it will be doing full science operations at the end of this decade. So it takes a few years to build, a couple of years to calibrate at least, and then it will be fully running. So what are we talking about? So eventually, after a lot of discussion as to what do we need and what do we need to build in scale, we end up with 2 telescopes, one telescope, one facility, but it needs to be in 2 different styles, if you like. This funny looking one here, which I'll talk more about, are log periodic dipoles. They look a bit like Christmas trees. They're about this tall, a bit taller than me. 130,000 of them strung over the Australian desert, the West Australian desert. Now that is for wavelengths between 50 and 350 megahertz. So from a few meters to a meter in wavelength. And then the other part of the SKA works at much shorter wavelengths, so this around the 20 centimeters to a centimeter, is based in the Karoo area in the South African desert. So two sites which you may spot, of course, are fairly unpopulated, so there's a natural barrier or a natural advantage to go into these types of sites in the world. And this is what multiple countries are investing in to build. So two arrays, they will use some of the same algorithms, some core ideas, but fundamentally they are actually two separate telescopes. I did want to show you some of the ideas that came along to get to this. So this is if you go onto the website, this is what you will see, as this is what we're going to get for our money. But along the way, there was a lot of prototyping. This is one of the Pathfinders, Pathfinders towards the low end, the low type SKA. This is the US thing called the long wavelength array. There is another one based on cross dipoles in the Murchison region. It's called the Murchison Wide Field Array. That's Australia, and a number of partners have built this. This is a significant telescope. It's at the SKA site, which isn't over on the west coast. The largest of the low frequency, the largest of the low frequency precursors and pathfinders is the LOFAR telescope, built, designed and operated by Astronomy. We're very proud of that because it's actually now spread across Europe. We've had 8 other countries buy stations from us, and we now have baselines up to 1,900 kilometers long. So it's incredibly long baseline telescope. It's called LOFAR, the Low Frequency Array. This is its core. This is the center of LOFAR. It doesn't look very much like a radio telescope. It's based in this area, which of course is very flat, being the Netherlands, but this is the core, and then all of the stations that you can see here are then linked to it in real time. And the fundamental antenna type here, we have 80,000 antennas in LOFAR across the whole system. The fundamental antenna type is this. It's in supported polystyrene. If you're watching closely, you realize that looks very much like the MWA or the L. These are just simple dipoles. But that's the low end, because we're working in meters or tens of meters of wavelength. There were some more exotic ideas, particularly for the mid-frequency range. And again, this was engineering, let loose, with creativity. Great. This is probably the most exotic one. It was actually called it's very fuzzy. I'm sorry it's so fuzzy. These are Lundberg lenses. So this is where you have a graded dielectric material that can focus radio waves. It is an idea. It is used in radar, but it was thought that we could adapt this for radio astronomy. And evidently this is a picture. This doesn't exist. Another interesting idea that came along was from Canada. And I realized it was so long ago, I couldn't find any PowerPoints about it. It was called the Large Aperture Array, where you would have a very flat area of collecting area, and you would float this thing called the Big Orange Balloon, a bob, with a receiver on it, 100 meters above the ground. Anyway, there was some prototyping that did go on, but not very much. But it was a very active era of new ideas and really pushing the boundaries. And perhaps one country that did push the boundary and actually built is China, because they built the FAST telescope. This is the biggest telescope in the world in single dish. It's 500 meters across. It's built in a natural depression. It was finished 2 years ago. And so the idea was the SKA could be built of maybe tens of these things, not just one, but tens of them. So China being China, they did indeed build one. They not only built one, they built a very nice hotel in the next door depression, which is very impressive. I have been there, it is stunning. Anyway, so that shows the scale, and each of these test areas or pathfinders I've spoken about generally have been single country investments and single countries pushing them, but towards the global endeavor of the SKA. Nevertheless, the SKA mid has settled, and this is a real picture. This is the picture of Meerkat, which is now built at the SKA site in South Africa. So for the centimetre radio astronomy, this is now built. This is 64 dishes, and the SKA mid will build that out to 200, 210 dishes, for at least for the first era. I realise I'm going on a bit. I had some movies. I'm going to skip my movies. Oh, there we go. There's SKA low. This is a simulation. Please believe me, this is not real. But this is to give you some idea of the scale of these telescopes, which are now spread over land, that relatively unpopulated, thank goodness, but to spread out these massive arrays in areas where we do have radio frequency spectrum protection from mankind, as it turns out, and this will be SKA low. I'm going to skip that, I hope. Right, some challenges which I think have been hinted at already. And we also see it in LOFAR, and I know other telescopes see it too. So the first one is just system complexity. Instruments of this scale simply cannot be understood by any one single person. I mean, you can in general. I mean, I have the general picture, right? I could teach you that in a day, I'm sure. But to find someone who really can bury down and find the fine details or know what's going wrong is really now lost. We moved from an era in the 1950s and 60s where there really was a heroic leader, someone who really understood the whole system from A to B. So we've moved away from that. And perhaps the thing that really strikes me now is that upgrades and any changes to these systems become very large and very slow, and with that, I'm afraid, risk. So the need to work steadily and slowly comes along. Now, that may not be a bad thing, but it does mean these telescopes are not necessarily very agile. So if something disrupts our field, something exotic is discovered, we have to think very carefully about how we respond to that. So they were the challenges I could think of. But it is all done by people. So here's my people slide. I'm always pleased to see people slides in these talks. So we have a great crew. And of course, it does come down to people and how we interact as people. So I'd like to just finish with some thoughts. So as we work in bigger and bigger subjects, bigger facilities and bigger projects, my question is, does big science change attitudes? Does it drive skills? Does it change the way we're skilled in how we actually work together? I do think there's more room for diversity and talent. I think different talents come to these big collaborations offering very different things. And I think also that talent also helps us reach out and perhaps inspire others. And maybe we lose something, I don't know. I haven't really thought. The one about recognition, I think, is an important point. It's certainly, these big projects involve big money, really, really big money. And it is difficult for an individual, and maybe this isn't a bad thing. The ego, or the egotistical leader, perhaps has gone. It is hard to make a mark, so you have to be very, very careful to know what your contribution was. And I noticed particular high energy physics has alphabetical author lists. Yes, Isabella's nodding, good. We don't actually, we still have it by contribution levels. So the first author is the person who's done the most work. Attribution, yes, attribution of who did what is difficult. And what does this do for careers? Well, we had a question on that this morning. So, don't know. But one thing I do hope is that I hope we don't lose our creativity just because of size, scale, and getting lost in the crowd. I put this one slide in because it's a very good Dutch-Australian story, I will tell you in case you don't know. Wi-Fi has its roots in radio astronomy. The original mathematical paper looking at the inversion of the Fourier transform was written at Astron by 2 Dutch and 1 Australian engineer. That Australian engineer went back to Australia, that's John O'Sullivan, and the Australian government ended up owning the patent to 802.11. But it does come from radio astronomy. And that small team, would that happen today? That's one I think we need to worry about a little bit. Small, very intelligent, very creative people, do they get lost in teams of 1,000 people? I hope they don't. I think we work very hard, and I think the sub-teams that Isabella and I know exist is important, and that we still need to make that contribution as humans. So, thank you very much.
Thank you very much, Carole, for a brilliant talk, and it's open for questions.
Anything.
Yeah.
Yes, I have some background in astronomy, admittedly at different wavelengths, but you asked the question, how do you get a big project going? And since we're the history and philosophy of physics, I think the history is worth mentioning in the case in a case in hand, particularly radio astronomy. The short answer for radio astronomy was you grab the losing sides technology after a war. Does this ring a bell?
Yes, so these
the
are
giant
the
Wurzburgs.
Yes, the Wurzburg dishes, that's right.
Were what formed the nucleus of both Cambridge, UK, and the Australian telescopes,
Yeah.
Which in turn was based upon the Zeppelin airship design, the circular ribs. So it was fortuitous, if you like, that it got going. And that's, if you like, a first point. I'll leave it at that anyway.
Question again.
Yeah. You touched upon the complexity of the systems that you are dealing with. And in complexity science, sometimes they talk about the cliche expression that small changes may produce large impacts, and sometimes large changes may not produce any impact. I wonder if in your complex systems you have come across similar behaviors.
Oh, I'm sure. I'm trying to think of an example. I think we still want to know which we're going to end up with. So your point is a small change may have a very big impact. And I think they're the good changes sometimes. We tweak a system, or someone says, if we adapt our processing, LOFAR can also do this in our instance. That's a fabulous outcome. But you need that creative person, you do need that expert who can see that benefit. So that's what I was really trying to get down to. We simply don't have anybody who knows the whole system end to end. But when we have talents that know, let's say, the digital signal processing really, really deep, they're the guys and girls that can make the impact, because they can make those small changes which really change the game. And they are the most creative, most productive people you can find. Yeah.
Carole, could I just ask, you mentioned the site selection for the SKA, but not much about it. Is there a great significance to it being in the southern hemisphere, or could it as well have been?
There's a slight significance in that the centre of the Milky Way is accessible from the southern hemisphere. Having said that, the driving science for the square kilometre, I didn't talk about how the square kilometre array actually down selected to that design, so I couldn't do everything in half an hour, sorry. But the two science cases were in fact detecting what's called the EOR, the epoch of reionization, when the very first stars and galaxies form, converge, and also timing pulsars in a network to test Einstein. So those two science cases, in fact, don't care about which hemisphere you're in. But there is an advantage to going to the south as soon as you say, well, okay, if you also want to do galactic centre of science, and you also have the big ESO telescopes, ALMA, in the southern hemisphere already. So there was an advantage, and there was the absolute advantage of these areas being relatively radio quiet. That was a big one. That's a big win.
I hope they're self-contained from the point of view of power, at least the South African one, because coming from South Africa, they have constant power cuts, as you know. So
that's a big discussion I could do at least another half an hour on.
There's a question here.
So, yeah, I have an engineering and a science background, quite big projects. The question of not stifling innovation is a really key one for moving us forward. we used to have two measures. We tolerated skunk teams who we knew were doing things, but we turned a blind eye. And the other was to formally say, Friday afternoons are for thinking and innovation. How do you think those sorts of concepts fit with modern big science?
Yeah, I recognise them. I do recognise them. Perhaps more formally, I think this era, and this is how we're approaching it at Astron, I won't say it's the only way, but this era gives us a different view again, which is, yes, we're contributing and moving the SKA forward, but at the same time, we also have at least a 10, 15-year vision for what next. We're actually looking beyond the SKA. We're already developing photonic systems and looking at the hardware-software balance in processing very much more deeply than is being built in the ground. And I think you're nodding, you see this in aeroplane design. You might be building the 787, but you're already designing the next one. So my joke about once we built the VLA, you think about what next, that is very much the case. Now, to me, that is the role of the national institutes, to have the vision and the talent. My guys are working on the next 10, 15 years technology today, and it won't be on a telescope for another 20 or 30 years. And I'm sorry, I forgot to say, and it's an important point, you can probably tell from these timelines, the SKA is a 30-year gestation project until it comes on sky. So it's just like any other big project.
Near the back.
So towards the end of your talk, you highlighted the impact on the people from these big projects, and we've heard earlier on the impact on the engineering and the way you build these things, but nobody has mentioned the impact on the data themselves, which are of course the raw material for scientific discovery. So I was wondering if you could comment, the data rate, for example, of the SKA is so large that you cannot save the data, so you cannot question the data later when a new question arises. And in astronomy, a lot of discoveries that were made were totally serendipitous. They were not what the telescopes were built for. So I wonder if you could comment on this fact, the impact on possible serendipity of these new telescopes where the data rates are so large.
Okay, that's something we're definitely working on. For instance, I will take LOFAR as the example. We do have the world's largest astronomy data store at 50 petabytes. And that is already at the scale there. We are learning hard how to compress it, how to keep it for those reasons, that the historical, go back and look at the data is important, and how to understand how to do that for SKA is vital. But it's a very good point that we're having to learn that we can't keep everything, and we need to learn and understand how to have, 5 or 10 minute buffers for when we do get an alert, say from SWIFT or some other telescope, to be able to go back at least some amount of time. It's really pushing us to think hard about what is it we need to keep, what is valuable, and how do we do that? Yeah.
Second.
Thank you very much. Great talk. Thank you. I'm a bit of a captive audience because I'm an amateur astronomer, both radio and optical. But I have found a lot of my colleagues and people come up to me because I'm the sort of local person that can tap on the shoulder, ask questions about a lot of big science projects, and particularly astronomy. And something like the SKA, being a radio astronomer, I'm a convert before I even heard the letters. But big concern is how to get this across to people who are genuinely interested in, but they're not engineers, they're not astronomers. So you've got the Hubble, it's a tube, it's in space, it's got a couple of solar panels either side, and they see the pictures that come out. With something radio astronomy, it's a bit more difficult. Elma's sort of halfway in between the two. Elma, how do you, give them something to visualise in terms of what SKA is physically, and also how to give them a perception of the importance of the work it's going to be doing and the different areas of astronomy that it'll be working in?
Yeah, I agree. I think visually, I think radio telescopes are at least as appealing as any other type of telescope, right? You can show beautiful pictures of big arrays. The question is then people say, why do you need that? Why do you need, the ELT? Or why do you need that and Hubble? So explaining the idea, the fact it's a jigsaw. It's a jigsaw of physics, and extending that we need those pieces of information. But it's a continual exercise. That's all I can say. It's continual part. And that's why I stuck in the Wi-Fi story, because there's also the one of, but why do we do this? And it's like, well, show me your phone, show me your GPS. How do you think it works?
Very good. Any more questions? Oh, one more.
I've always been involved in the preservation of science and scientific instruments. And it seems to me there could be advantage from the public's point of view in visualizing what it is that we're spending very, very large sums of money on. Now, these objects seem to be visually some of the most impactful that one can think of in recent science. I want to know, has there been any feeling that some perhaps redundant radio telescopes should be preserved for that particular reason?
The simple answer is yes. There are radio telescopes that are national monuments. In fact, the one at Dwingelo is a national monument. So keeping them as, or preserving them as national monuments, yes. I don't know too many that have been closed down, I have to say that. Big discussion in Australia about Parkes, which keeps going. It's a beautiful telescope. So I think that's right. They do need to become engineering monuments. They push the boundaries when they were built. And to keep them, but then we have to add the exploratory, I'll put it to this gentleman, we have to make sure that people understand why they were built and what they achieved. And sometimes I guess it also sounds a bit too incremental. So we have more to learn, I think, here. And I do think radio astronomy has this that everyone thinks it's a bit exotic, you know. But we can make pictures, we can make beautiful pictures.
I mean, even doing radio is being taken apart.
Yes.
Which is a big sculptural object.
Yeah.
One final question.
Yeah, so on your final slide, you included communication as one of the big challenges, or the challenges in big teams. Could you sort of expand on how you think you can tackle that?
Well, sorry, I missed your key word. You said something was the big challenge?
Communication.
Communication, yes.
Ironically, yes. For example, so we had a lot of problems trying to get students to update a wiki page. And of course, these days you think, oh, they're all digitally keen and they would be like that sort of thing. So how do you...
Okay, well, I'll say it because I know our friend from CERN didn't say it, but I think the World Wide Web was one of the evolutions, innovations that came out of CERN to start all of this revolution. But I think you also hit the point that we now have so many tools and they're still at the end of a keyboard. That's not communication. Just because I type something in a wiki or a web page, that's not communicating to my fellow team members. And I do think that this training of how you truly communicate as a scientist and as a person, you know, perhaps two different levels, is still a core skill that we must remember we have. Just because 1,000 of our collaborators, you know, they read the web page, they read the wiki, you know, or whatever we use, Team Center, that's not enough. Communication is still people to people. But it's something we have to keep learning. And I'm afraid, and I only say that because one of the things we haven't spoken today is about green sustainability and all the issues that come around travel and the fact some of us have travelled to come to this meeting. But you can't beat face-to-face sometimes because you can't work with people completely remotely. So communication still requires us to be humans in a room.
Also, you have your project spans 30 years, so having the early experiences, you said yourself, having the early experiences available to the later generations
there's a hell of a lot of documentation, that's right, but that's not the same as communicating, necessarily communicating on the human level of this is what we really did learn. And it also, you're right, it picks up on this one that many of these big projects are instigated and carried by a generation that does not use them. And that's actually, the SKA will be the first of these for the community I live in, that it's really been, you know, brought up and supported and brought to reality by a community that is, I'm going to say my age, that, you know, frankly, are not going to be the key users of the SKA. It's our students that are going to be the key users. How do they accept it? How do they flourish? How do they learn? How do they love it?
Good. Let's thank Carole again for a beautiful talk.